curl and divergence and surfaces. Questions?
Number for 16.6, number 20. I'm just, so to figure out the equation of the plane,
Yes.
will we do the cross product of those vectors? That's the one vector, or is that easier to do it?
There's an easier way in this case. So let's think about a plane that we know contains two vectors. A plane that contains two vectors, right? So if I have vectors v1 and v2 and some point p0, I could say the equation for the plane comes from looking at the normal vector. Yes? But I could also say that I'm going to make a grid on this piece of paper using these two vectors as axes. So let's consider, if I take these two vectors and I add them, where do I end up? Right? First do this one, then do that one, we end up over here, right? I could consider that the sum of one copy of vector 1 and one copy of vector 2. Yes? But that means if I went this way instead, I could think of it as negative a copy of vector 1 plus vector 2. I could think of all of the possible multiples of vector 1 and all of the possible multiples of vector 2, right? What if instead of using whole number multiples, I used fractions or irrationals or any number I wanted, right? Could I figure out a way to get to this spot right here? I could use some fraction of the first vector, some fraction. How about this spot over here? Or this spot down here, right? I could cover this entire surface by starting at the point we were given, adding some multiple of the first vector to some multiple of the second vector. Let me call the numbers I'm multiplying my vectors by S and T. Aren't those parameters? I don't have to get the equation of a plane to look like this. I can say, oh, wait a minute. I can think of any point on my plane as the starting point plus some multiple of the first vector and some other multiple of the second vector. And then I've got a two-parameter family. Like U and V is my R of UV, only to be defined in terms of vectors. This is the same definition I used for a subspace in linear. The subspace spanned by two vectors, only the point was always 0.
Say that you got the first equation.
That would be right, as long as you got it correctly. That's a good equation.
But yeah,
Right? And then I would plug in the point to figure out what D is. That works perfectly well. That absolutely that'll give me one equation in X, Y, and Z. And then if I rewrite it to be Z equals, I'll have two variables, won't I? That works. The advantage of thinking of it this way is that I don't have to go through and do the cross product. It works, but I don't have to. Can you get like that? More questions? This one. Yes.
I was like, well, we use one variable to use, you have like X, Y, and Z and theta, but you need like another one for like N.
You say that's too many variables. X, Y, and Z and theta, right? Or are you trying to write X? So I'm gonna end up with two parameters. I want X in terms of two things, Y in terms of two things, and Z in terms of two things, right? So let me see. This says the part of a cylinder, oh, sorry, the part of the sphere, no, cylinder. Between two Y planes, yes? All right, wait a minute. This sounds like the picture we drew yesterday. Right? So here's my crappy picture. Do the X and Z values care about which Y we are at? So I could do that with going around a circle. I could go around a circle over there on the left, or a circle over here on the right, or a circle somewhere in the middle, yes? With that in mind, how should I parameterize X and Z? How about going back and forth, left to right? A separate variable, right? Something that doesn't care about what theta is doing. I written my variables in Y and theta. I think yesterday I did the same idea, right? With 2 and 2, only it was U and V. So it's cosine of V with sine of U and then V here, right? You want to call it V, you want to call it W, just don't call it X, Y, Z, or theta. You've already used those letters. Sure. As long as that's the right radius. Is that the right radius for my sphere, for my cylinder? Circle of radius 3? As long as you think so, that's what I'm going to run with. More questions. Ask me more things. Go ahead, man.
So for 16.634. You have to take the cross product of the derivatives with respect to U and V.
Yes.
I plugged in the numbers for U and V before I did the cross product. Is that important?
Absolutely. Because we're taking it at that point. I can use those numbers. If I was taking it in general and then figuring out for that one point, then the cross product would be a lot messier. I'm much happier doing plug in the numbers first. You're still looking at me like I've lost my mind. Talk to me.
It makes sense, but it doesn't.
So walk me through what you've got then. Okay, so what is the R equation again?
U squared plus 1, then V cubed plus 1, then U plus 1.
So what's RU?
Yep, 2U, 0, and 1.
And RV?
0, 3, V squared, 1.
So I'm gonna do it the hard way. RU cross RV I do that, right? And then when I was done, I would put in whatever the U and V values are. What are the U and V values? Say again?
But two,
U is 2, V is 1? Because we're at the point 5, 2, 3. Okay, so if U squared is 5, then U squared plus 1 is 5, U is 2. And yeah, okay, I'm good with this. Okay. But if I plug those in first, then I get 4, 0, 1, and I get 0, 3, 1, right? If I do the cross product with these, I'm getting a single vector. And it's the vector that's only good to spot 5, 2, 3. If I do this cross product, then I can put in any U and any V later, right? Works both ways. If I plug in those numbers after I'm done with all the cross products, I should get the same thing as if I do the cross product with just these in the first place. So I times 0, 1, 3v squared 1 minus j 2u1 0, 1 plus k 2u 0, 0, 3v squared, right? So that's what, 6uv squared. So that's 6 times 2 times 1, that's 12. But if I do it with these, it'll be 4 times 3. Isn't that 12 also? It's going to work out the same whether I plug in the numbers first or I plug in the numbers last. Because I was asked to find this at a specific point, I find it easier to plug in the point first.
so then that answer you get, we just multiply. It's the,
That's the normal vector. So that means that that's the normal vector for my plane. Right? That's the ABC. And then the equation of a plane is n dot r minus r naught equals 0. You just found n. The r naught is the point you were given. So that's x minus 5, y minus 2, z minus 3. And then whatever you came up with for your normal vector. That was on exam 1, that formula. Now you know why we keep the index cards. Right. If I'm given a parametric surface, I'm going to do the double integral RU cross RV du dv. And if I'm given a function, I'm going to do it like that. And then maybe this will be easier to do the x dy or dy dx or in polar or something. I don't know. And that's over R. The advantage is that this version in parametric coordinates over here is a generalization of this version here. Because we figured out when we were doing tangent planes, we said, oh, wait a minute. I have partial with respect to x and partial with respect to y. And I take the cross product of those, and the vector that goes this way, and I take its length. That's exactly what this is. That's the length of a vector. It's this vector. The same friggin' thing. I just changed coordinate systems. Which means way back here, if I want to find the surface area of this cylinder, I can do it in theta and r. Sorry, theta and y. Which makes sense. Isn't it the circumference times the height for the area of the cylinder? Change in theta, change in y.
So what's the data in mind?
Because I'd use theta and y down here for my variables. Because those were my parameters. Once you decide how the equations were given to you. Oh, this is a set of parametric equations. This is a functional equation. How do you do with that? Now, again, this is my statement. This is the length of that vector. Because the partial derivative with respect to x is gx 0, 1, and the partial derivative with respect to y is 0 gy 1. And when I take the cross product, this is what I actually get for the length of the cross product. So I really am doing it that way for my parameters of x and y. This is one of the downsides, in my opinion, and this is a very, very, very biased opinion, of teaching you all functional notation first. If I did everything parametric from the very beginning of Calc 1, I'd never touch this formula. I do everything. But that was Newton's version, and we got in trouble with the church, so we couldn't do it that way. 4 questions.
Fifteen 43. I got the integral of the root of 1 plus b squared.
Like this. What are my limits of integration?
Yeah, 1 for 0.
Okay. Well, there's no v's anywhere in here, right? So I'm going to take that out. Now we go back to chapter 7. And I ask, how the hell do I do this integral of 1 plus u squared under a square root? Chapter 7, section 3. Remember that? One plus u squared. A squared plus a. There's my substitution right there. Page 486. It's a long time ago. Like October. Alternate option. Remember all these integral tables in the back of the book? I promise I'm not making you do something impossible. I can't remember all the stupid tricks. When I'm subtracting under my square root, it's either sine or secant, depending on which is first. When I'm adding under my square root, it's in plus with like a little t. So the way I remember that. What's your option of last resort? I go to Wolfram Alpha, I plug it in, I go, okay, this is the antiderivative, and walk away. Do I recommend that? No, we should practice the tricks so we remember them better. But it was October when we did this, man, I don't remember. More questions. When you run out of questions, I brought toys. Let's think about it.
16.5. 16. Finding the lowercase function.
So 16 says find the potential function, right?
Yeah,
So my first question is the vector field conservative? So the curl worked out to be 0.
Yeah.
Great. So with that in mind, the vector field was, give me the vector field if you would.
I plus sine v j plus y cosine v.
I sine zj, y cosine zk. Okay, so this is f with respect to x, this is f with respect to y, this is f with respect to z. Because you know it's conservative, those are my pieces. All right, well then, according to this integral, what's f? Plus some constant, maybe with y's and z's in it, right? Okay. According to this, what's f? According to this, what's f?
Y.
Okay. Can I make all of these work together? Where's the y sine z in this part? Where's the x in this part? Because that could have constants that are x's or z's or both, right? Same thing here. At this point, I put my hump on. It worked, master. It worked. That's Renfield from the Frankenstein, Dracula movies, or Igor from the Frankenstein movie. Igor the Hunchback. That film is older than both of us put together, so. Or if you'd rather go watch the young Frankenstein version with Marty Feldman playing Igor. Igor. And the hump moves from side to side. In different scenes, they put it on different sides of his shoulder just to with people, and it made it all the way through the film as a gag. More questions? This is the preview for tomorrow. How many sides does the sheet of paper in front of me have? I took a strip of paper and I glued it, I taped the edge together, right? That's what I did here. Notice the difference between the two. This one, before I glued tape the end together, instead of just wrapping it, I twisted it. If I take a pair of scissors and I cut down the length of this, what's going to happen? I'm just going to cut all the way down the middle of this strip. I'm going to make two of them. Because when I finish cutting, it'll fall apart. Make a cut in the middle of the strip I gave you that's got a twist in it, and I start cutting. Just keep cutting right down the middle. Oh, there we go. Now I'm back to where I can finish the cut, right? Right there. Cut all the way through. I didn't make two. Same idea. A band with a twist in it. I'm not going to. It took my friend quite a while to make this, but I did put a pin in one edge, right? Put a pin here by my fingertips. So from your perspective, the pin is on which side? Sorry? Well, it's on your right or your left? On your left. I am now holding my other hand. Start turning the star. It clearly can't change sides. Stop. Not on my fingers anymore, it's on the other side. Holding my other hand, keep going. Stop. How many sides does that object have? It doesn't have a left side and right side. It has one side. The strip I gave you, the thought experiment, a gentleman by the name of Mobius. It is a surface on which the idea of left and right doesn't work. On which the idea of front and back doesn't work. I made these from old exam papers. Hey, look, show that this vector field is conservative and find a potential function. I made it from a Calc 3 paper. But you can see the side that's printed on, right? But as I start reading the question, I end up on the other side of the paper. There's no front or back to this. There's no left or right on this shape. It's got one side. Why am I bringing this crazy item up? We defined an idea of a vector field moving across a curve. We did an integral f dot n ds. that measured how much of my vector field went across the surface. And we said in order to make this work, you needed a simple, closed, positively oriented curve. That was Green's theorem. My goal tomorrow is to extend Green's theorem to work on surfaces. I want to know how much goes across a surface. Means I need to know which side of the surface is the front and which side of the surface is the back. We're going to call a surface where I can do this an orientable surface, a surface on which we can put an orientation. The Mobius strip is a non-orientable surface. It, as such, can be drawn in a number of different ways, and if you'll notice, the edge of that surface, well, from 0 to 2 pi, it only goes part way around because we switch left side and right side here. My favorite version of this was by the painter M.C. Escher. Are the ants on the outside or the inside of the strip? The answer is both, because there's only one side. (1963). I'm going to work on surface integrals. I'm going to try and figure out how to do integrals like we did on curves. I'm going to try and do integrals on surfaces. I need to look at surfaces that have orientations as opposed to those that don't. By the way, another tricky idea, instead of cutting it in half, I'm going to go a third of the way over, roughly, and start cutting. As long as I stay a third from the edge, as I continue my cut, what's going to happen? Well, first thing is by the time I get back around, I haven't met my cut because it changed sides. What do you think is going to happen when I actually do finish the cut? When I cut it in half, I got one bigger one, right? If I were to take a regular cylinder and cut it a third of the way, I get a third and a 2/3, right? But I get to go around once, I went around twice. The middle third is now detached from the edge. It wasn't one edge, it was both edges. That's why one of these is twice as long as the other. Surprise!
The little one also.
Yes, the little guy is twisted. But notice something interesting, the outside one is twisted more than the inside. Count how many twists there are. There's an entire magic routine called the Indian scars. Again, I don't know why they put it in India, maybe because the Europeans were all, ooh, the ancient mystical East sort of bullshit. But they called it the Indian scar routine, and they would go through and cut up stars that had been pasted together like this. This one, by the way, this knit one, was actually not knit flat. It was knit in the round by casting onto a pair of needles connected by a loop of wire. And you actually have to cast the stitches on twice, and then it's knit from the center. You can see that more clearly on this one, where you can see on the same side, you've got the knit stitches and the purl stitches, because all you did was keep knitting and knitting and knitting from the one starting point right here in the middle. Bordhi, Bordhi, created the cast on for Mobius scarf construction. And one of the more neat conversations I've ever had in my entire life was three mathematicians and an editor going, wait a minute. Apology of that is, how do you know whether it's going to be right-handed or left-handed? And if you glue two of them together, what happens? Imagine instead of doing this with a flat strip of paper, you take a tube. Take a tube and glue the ends together. What do you get? You get a donut, bicycle tire. What if before you glue the ends together, you twist one of them? You get a tube whose outside is on the same size as its inside. That bottle has a volume of 0 because the inside and the outside are the same size. If you cut that in half, each half is a Mobius stamp. There. I got one of these for two, but it's for Christmas a number of years ago, but it's glass and I didn't want to run the risk of bouncing it around and breaking my own. I think if you look at the image of my face on canvas, I'm actually holding. My favorite version though is he makes hats. I have to go back inside. Anyhow, we'll talk more about surface integrals tomorrow. I will see you all then. Bring your homework. If you have additional questions, I'm going over to my office hours. Ta.